So I want to finish Gromov's theorem today. And so let's write down everything we know, the background. So first of all, Ozawa, we have Ozawa's theorem. I'll keep on the board so that we can use. Ozawa's theorem says the following: if G is amenable, finitely generated amenable, then one of three things, and we have a second moment random walk, then one of the following must hold. Again, they're not mutually exclusive. They're not mutually exclusive. So one is that there exists a non-constant Lipschitz harmonic function such that the variance, we can even write here the suprem over x, so the variance of h of xt, divided by t, converges as t goes to infinity. Oh, this was one. Okay, two, I'm not going to have enough room, right? Two is that G has a G is virtually indicable. G is virtual. I will repeat what indicable is. Virtually always means it's just a group property that holds only on some finite index subgroup. Okay, so that's all. And three is that we have the G has a nice representation. So we can think of some quotient of G as a group of matrices. Okay, so there exists a normal subgroup in G such that G mod n is isomorphic, say some U, which is a subgroup of UDC, so finite dimensional vector space. Okay. Now let us see what we can do with these things. And in order to deal with these things, we need a few algebraic theorems. Okay, let me remind you what indicable is. What is indicable? Is indicable. Last time we explored this, if and only if exists homomorphism from G surjectively onto Z. Surjective homomorphism. Okay, we showed this is true, and this is equivalent to G has abelian quotient non-trivial abelian quotient. Right. As soon as you have a non-trivial abelian quotient, you, since G is finitely generated, you have a finitely generated abelian group. It has a coordinate that projects onto Z.
Yeah, what's the D is the index in number 3. Do we get the D from the index or?
There's no index here. Just has some quotient, which is a unit.
Yeah,
the D is the dimension of the invariant vector space that you act on in the Hilbert space. So if you act on a finite dimensional in a unitary, if you have a unitary action and you have a finite dimensional invariant space, then you're basically your group is isomorphic to up to modding out by the kernel. Your group is isomorphic to the some subgroup of the unitary matrices. Okay, this n and this n are not well. There's no n in number 2. There was an n. They're not the same n. They weren't the same n in the previous thing.
In the like one time when we stated it, there was something about the finite index and not finite index. Is it like where can we see?
Finite index comes in here. Virtually means finite index. Virtually means finite index. There exists an indicable subgroup of finite index in G. Okay, and then here I'm explaining what indicable.
You mean non-trivial infinite abelian quotient, right? You can have finite quotient, abelian quotient.
Infinite abelian quotient. Right? This is equivalent to being virtually indicable because any finitely generated abelian group has a surjective homomorphism to Z, and you can compose homomorphisms. So if you project onto an abelian group, then you can project onto
Yeah,
Z.
we're talking about
Everything is finitely generated.
everything is
Okay. And these two are equivalent to G being a semi-direct product. Okay. Or some group N. Now, N does not have to be finite, infinite, finite. It could be, in fact, G could be Z itself, right? Z is indicable. Identity map is a okay. A semi-direct product, I'm going to remind you what it is in a second because I want to give an exercise. Assume E has polynomial growth of degree. What does this mean? I'm going to explain because I was a bit loose or I didn't maybe define everything. Polynomial of the degree D means that, or of degree at most D, let's write it this way. This means, okay, let's write of degree D. So this means that the balls of radius R in G grow at most like a polynomial of degree D. So their volume is at most like some polynomial of degree. Some polynomial of degree D, it bounds, when you evaluate it on radius R, it bounds the size of the ball of radius R, okay? Assume also that G is Z acting on some N. Okay.
Do we know? I'm sure we know, but just for like feeling what the growth of Z to the D.
What?
What is the growth rate of Z to the D? D?
Polynomial of degree.
Polynomial of degree D. Okay.
Exercise. It's easy. It's an easy exercise.
Yeah. I would.
When you choose your, you can choose whatever generators you want. Choose the standard generators. It's the easiest to work. Then just count. Not very hard.
Yeah, I think we didn't define yet growth of a group.
We define growth.
Define growth?
We talked about growth at some point. Equivalence class of functions. So assume that, but this is a polynomial growth. It just means there's a polynomial boundary. It doesn't. Okay? Assume that this is case. Fact, which means you can assume it. I'm not asking you to prove it. Fact, N is finitely generated. When I said that I assume that G has polynomial growth, I also assumed that G was finitely generated. There's no growth without finite generation. Okay? So fact, N is finitely generated. This is going to be a corollary of the theorem that I'm going to write down on the board in a minute. Proof, what you do need to prove, is that N has polynomial growth of degree at most D minus 1.
The one from Z.
The one comes from Z, yes, but it could even be smaller, but at least one smaller. Okay, and what you have to do is you have to remember what a semi-direct product is. I told you what a semi-direct product is. Maybe I'll write it here just to remind you what a semi-direct product is. A semi-direct product. What is a semi-direct product? This means every G and G. So, sorry, there exists some letter A, okay, in G, such that for every G, there are unique that be Z and G in the subgroup N, okay, such that G can be written as M G A Z G. You can write your whole group. There is a normal subgroup N, such you can write. I should write here maybe. It's basically the same normal subgroup, but you have to look at it differently. So here there exists a normal subgroup N, there exists an A. So this is what a semi-direct product is. It means you can write your elements in a unique way. There's more than one way to do this unique decomposition because there's more than one way to choose A. Int A is the element that get maps to 1 when the projection onto Z.
A represents an automorphism.
Yes, A represents an automorphism, but you have it turn the action into a conjugation.
So this is an inner or outer.
It becomes inner in this group.
Mhm.
Here it's it's
Action.
any automorphism. It could be, so Z acts on N via some.
It becomes an inner automorphism.
How do you create the semi-direct product? You have an automorphism acting and you look at pairs, or you artificially create the letter A and you write your group as all the elements of this type and you have to prove that that's a group. Okay, you add the new letter A with infinite order, coming from your automorphism, and you make it conjugation by A of an element in N is exactly the automorphism action, and you can make it an inner automorphism in this group. Okay, that's how you do it. But here this is kind of one way to define what does it mean for G to be already a semi-direct product. I didn't ask you to come up with the automorphism. Get it for free. They tell you there is at least one A that does this. Maybe there are more. Okay? There usually are more.
Now do you see this from the homomorphism criteria? You just take the quotient and then.
So I have a homomorphism that projects onto Z. I just take any element that maps onto, I take N to be the kernel, and any element that maps onto 1 in Z, which is a generator of Z. Then I can prove this.
So is it from
Okay. This is just algebra, and I don't want to go into it too deeply because I will spend too much time.
So A is from G or from N?
A is from G. G is you got a group that has this structure. That's what I said.
You take one.
Get a group with this structure and then prove this exercise.
That you take one from the kernel.
Not from the
And
kernel.
to be the kernel.
The kernel is what maps to 0 in Z. You take one that maps to 1.
Okay.
So it generates an infinite.
It's not from N.
1 in Z is not the identity of Z.
Yeah, no, that's
I think that N is going to be the kernel.
And it's
N is the kernel of the homomorphism.
which maps to 0.
But I said, if you have already this structure, you have a group with just some normal subgroup and some element such that you have this unique decomposition for every element in the group. Okay? Then prove that, and now you assume this group has polynomial growth. I tell you for a fact that N is finitely generated. Automatically, it's going to be finitely generated.
Because of the polynomial
Because, well, I'll write down the theorem in a minute, the precise theorem. Because of the polynomial growth. It's not true in general that such a thing, that this has to be finitely generated. Okay, Lamplighter on Z is Z acting on something and it's not finitely generated, that's something. But for sub-exponential growth groups, it is true that N has to be finitely generated. And then I want you to prove that in this specific case, N will have polynomial growth. Just count the number of elements using this decomposition.
What the Lamplighter exon is not finitely generated, but when we look at the Lamplighter, it only has finite support, and
So together with you can have an extension or a Z extension, meaning Z acting, and then you create a semi-direct product with a non-finitely generated group, which will become a finitely generated group. Okay, you should think another way to think about Lamplighter is maybe sophisticated. Think of the group of all finite support permutations on the natural numbers. This is a group not finitely generated. Transpositions cannot generate each other, and you have infinitely many of them. But now add to that the shift and its inverse, just the infinitely supported one permutation and its inverse, okay? The shift. Right, so this is a Z action now. Together now you have finitely many, you can generate with just one transposition and the shifts, everything.
And also you can take the free group, you take the free group and some homomorphism to Z, like take one generator and map it to.
Yeah, so there,
And
to
the
see that the
kernel-
kernel is an
the kernel
infinitely
is-
generated free group, it's harder to see. I mean, everything is easy, but you need to, now we would have to transition to talk about groups, and maybe it's another course in group theory that Yael should give. Yael Glasner, maybe should teach.
He gave.
Well, we should do it every semester. Because there's so much to say about groups, just discrete groups, there's so much to say. Okay, so that's the exercise. Let me write the theorem that I was talking about before. This is a theorem by somebody called Rosette, and I hope I spelled the name correctly, and maybe I do one S, two T. Rosette was a professor in Tel Aviv University. I think he passed away already. The theorem is the following: if G is of sub-exponential growth, G is finitely generated. There is a sub-exponential function which controls the size of the balls of radius r. Okay. For example, polynomial growth is sub-exponential growth, but of course there are other functions. And if N is a normal subgroup of G such that G mod N is solvable, okay, whatever that means, okay, then N is finitely generated. This is a theorem. Okay. Then I will add a fact to this theorem so that I can complete. Solvable, divided with the abelian implies solvable. In fact, this theorem, you just really needed to prove for abelian, and then the transition to solvable is in some simple induction. But in any case, what this theorem tells you is if you have an abelian quotient and your growth is not exponential, then this is finitely generated. Or in a different saying, what's an abelian? The abelian quotient here is Z. Okay, so any semi-direct product Z acting on N, okay, if N is not finitely generated, this will have exponential growth. Cannot get sub-exponential growth that's why the lamplighter has exponential growth. Or the permutation group I mentioned has exponential growth. Cannot get sub-exponential growth. So in this case, where we have polynomial growth, that the theorem, Rosette's theorem and the fact explain this fact. Okay? They just give you for free that N is finitely generated. Okay?
Are we going to prove it or?
What?
The
No, I'm not going to prove it. We can prove it, but there's a nice trick to it. It's not going to take long. Let's spend an hour to prove it. It's all the details. But it's like an algebraic proof. I mean, there's a trick by Milner that you do.
Also like a correlation between the growth and some like formation.
Yeah, but this one is like a simpler one. Yeah, but it's a nice thing, but you have to. I mean, show you the main trick in the proof, but. Well, let's see if we have more time, then we can add it. Okay. Okay. Let me give some more algebraic facts. Okay. About semi-direct products. So I need some more facts. This is a fact. Fact means a theorem I'm not proving, but it's not even like a real theorem. It's easy to see if you know the definition. So it's very easy. If So if Z acting, sorry, if N, if I have some group N is virtually nilpotent, then Z acting on N is virtually solvable. I will need this. Right? This is easy if you know the definitions, because what this means, up to passing to the finite index, which is easy to do, okay, because if you have a automorphism acting on N, and you have a finite index subgroup, you can pass to a further finite index subgroup, which is characteristic, so the automorphism preserves it. So you have a finite index subgroup sitting inside this thing, which is Z acting on, say, M, which is a finite index. And that will be finite index in this one, the big one, okay? And then you see that the commutator of that subgroup lies inside the M. So you have a group whose commutator is nilpotent. Any group whose commutator is nilpotent is solvable. That's just immediate from the definitions of solvable and nilpotent. I'm not going to go into what these things are. I don't really want to do that. And one last theorem, which is important for us. This is the deep theorem, the Milnor-Wolff theorem.
All this solvable part is just because we have an abelian quotient, like it's like more general, like because of the second fact.
Okay, I might spend some time talking about nilpotent and solvable. At the moment, I don't. So just what you should keep in mind is that nilpotent has to do with centers. You take the center, you quotient by the center. You look at that, you see another center, you quotient by that. Keep going. If you can end infinitely many steps, then it's nilpotent. Solvable has to do with commutators. Take the commutator subgroup. Oh, you look at that. You take the commutator subgroup of that. Look at that. Keep going. Okay. That if that ends infinitely, that's solvable. And together, if you just put these two definitions together, then if the commutator is nilpotent, the whole group will be solvable. Okay, and nilpotent implies solvable. So, and this is easy because the commutators, when you go down, they forget what happened, right? They only meet. So if the commutator is solvable, then the group is solvable. And nilpotent implies solvable. If the commutator is nilpotent, then the group is solvable. I mean, but you have to remember, nilpotent has to do with centers going up, and solvable has to do with commutators going down. Okay? That's all I want to say at the moment because these are big things. Milnor-Wolff tell us that solvable groups have a very, 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 very strict structure to them. Okay? Solvable groups are what you can create by taking abelian things and piecing them together. Okay? So if you have two abelian groups, you can take the and you want to take semi-direct products of them. Then the world you get, where you close all, you start with all the finitely generated abelian groups, and you close it to semi-direct products. And what you get is the world of solvable groups. Okay?
What do we start with?
All abelian. Okay? And you close it to semi-direct products like these things, but more general. And then you get solvable. That's what solvable is. So Milnor-Wolff tells us that if G is a finitely generated solvable group, there's a dichotomy, okay? Then either G has exponential growth, meaning the balls grow at least exponentially, okay? Or these are mutually exclusive. G is virtually nilpotent. Why are they mutually exclusive? Because virtually nilpotent groups have polynomial growth. This is a theorem of Wolff. So you can hear that or G is virtually nilpotent, and therefore polynomial growth. So these two things are mutually exclusive. Okay, this is the Milnor-Wolff, famous Milnor-Wolff theorem in 1968. Wolff proved in 1968 this. Any virtually nilpotent group is polynomial growth. And they both proved in separate complementary papers somehow that, well, each one is basically a proof of this theorem, this dichotomy for solvable groups. And Milnor asked in 1968, Maybe that's true for all groups. Maybe every group is either solvable, exponential, or polynomial in group. And he also asked, is it true that nilpotent groups or virtually nilpotent are the only examples of polynomial growth? Both questions were answered no. So, and in the 80s, beginning of the 80s, Grigorchuk produced a group of intermediate growth, and in the beginning of the 80s, Gromov proved that there are no other examples of polynomial growth groups because any polynomial growth group is a virtually nilpotent. So everything basically started at the end of the 60s with this 1968, there were like 3-4 papers published. This thing, one or two by Wolf, and 2 by Milner. Milner had proof of this theorem, and also there was an open problems list in some American Math Monthly, and some of the problems were by Milner, and he asked those 2 questions that I mentioned.
What did Gromov answer? What question?
Milner asked, are there other examples of, well, he guessed that there shouldn't be, but they weren't able to prove it. Can you show polynomial growth? So you know that all virtually nilpotent are polynomial growth, but are there others? Maybe there are non-virtually nilpotent. Gromov proved no. Gromov proved
Yeah.
equivalent.
This is Gromov.
Yes, this is Gromov's theorem. Okay, so we're going to use all of these to put things together and prove Gromov's theorem. So the first thing we want to do is do the induction. Okay, I'm going to erase this, but hope you remember it. Let's do the induction. You know what, that's in order. So theorem, and this is basically Gromov's theorem. This is the main part of Gromov's theorem. This is the hard part of Gromov's theorem, okay? Theorem, initially due to Gromov, but of course the proof we are providing is an amalgamation of the many different proofs over the years. Every polynomial growth, meaning also finitely generated, right? G is virtually indicable, meaning has a finite index subgroup, right? Has a finite index subgroup with a surjective homomorphism onto Z. Okay, so this is the first theorem. And this is the first, like, main, really tough part. Why? This is really going from some geometric condition to an algebraic condition. Homomorphism onto Z is a completely algebraic condition. You have to suffer this virtually always, right? Because virtually doesn't change the growth. So you know, if something happens for finite index subgroup, you cannot characterize growth without allowing yourself to pass the finite index subgroups. Okay? So let's see why this is true. For this, we need one more input that I didn't write down. Let me put it in now. Okay, so theorem. This is basically a theorem of Jordan. So how could it be Jordan? This is way before Milner. Okay? So Jordan did this for finite groups, but the method basically good for infinite as well. And in fact, there's much more known. So there's a much stronger theorem than this theorem known. Maybe I'll write it down just for posterity so that we know that there exists this theorem. Okay, but Jordan proved the following. Basically proved the following thing, and I think the refinement that I'm going to talk about was done by Terry Tao, so he put it on his blog or something. It's some refinement. So Jordan's theorem is the following: if G is a subgroup of unitary matrices. Okay, so unitary matrices. Remember, we have a lot of structure, right? Because we know how to do linear algebra. This is much more than just having an abstract group. Okay, so if I have a subgroup of unitary matrices and G is finitely generated of polynomial growth, then G is virtually abelian. Okay, so if G is an infinite group, such group, so Jordan proved it for finite groups of unitary matrices, okay? But if G is an infinite group, this means that G is virtually indicable. right? Any subgroup of any infinite subgroup of unitary matrices of polynomial growth is virtually indicable. This proves this is exactly this theorem for what? For unitary groups. Okay? This is, so this is the case for unitary groups. So this is Gromov for UDC groups.
For virtually indicable, we want the quotient to be infinite, right? And
if G is a infinite group of unitary matrices, right? And it's virtually abelian, the finite index abelian subgroup sitting inside has to be infinite because it's finite index. Right? So that's, you have a finite index abelian subgroup that projects onto Z, that's it. Good. So this will this was well known. It goes back to Jordan that for matrices we are done. In fact, let me write down theorem. This is by Jacques Titz. Okay, very important theorem, which is much stronger than this. And this says that if G,
it's building.
Yes, same guy, but this is called the Titz alternative. The Titz alternative is this theorem, okay? And if G is GLD, in fact, it's true for also other fields, but I don't want to get into exactly, for finitely generated, then if you go to the locally compact, and there are lots of works on this, Immanuel Boyard, too many things that I don't know about this theorem, and this is much more complicated. This proof is easy. This is a combinatorial proof using distance to the identity, using the ring structure of this of these things and operator norms. Very easy. Okay, this is much more difficult. This uses Zaritzky topology, okay? Which is something I don't even know what it is. I don't know anything about. So,
not also.
What? Well, it's a difficult. It's a new concept. I would need to talk about it, introduce it. This, I could do if I had a bit more time. I could just do it there on the board, using everything you know from linear algebra. Zaritzky topology is not something you learn in undergrad. Okay, that's my distinction between elementary and non-elementary proofs. Right.
So, unless you're doing the course with Ishai.
Well, okay, yeah. But you don't do it in first, second year, right? Everything that you do in mandatory courses in the math track, okay? So I think Zaritzky topology is a more advanced thing. Not completely out of the world, but it's just more advanced, that's all. Not elementary. So G is, this proof I could do after Nadav teaches them, linear algebra 2. Okay, this I can do the proof. Of course, there's a level of it will take more time for first year students, but they have all the knowledge to understand the proof. That's what I'm saying. Okay. So the Titz alternative is the following: if you have a linear group, so this is just a linear group is just a group of matrices. Okay. Then finitely generated and infinite. Then either finite infinite and amenable. No. Let's write the correct one. Then either it's an alternative, so they're going to be two mutually exclusive things. They're either G contains a free semigroup on two elements. And specifically, since we're talking about finitely generated group, think of the Cayley graph. Take those two elements, generate some, take some generating set with those two elements, write down the Cayley graph. There is a binary tree sitting inside the Cayley graph. This is non-amenable, right? You cannot make this amenable. Okay? In locally compact groups, you need to talk about closed subgroups. So you could, but this already proves, and so, all right, specifically.
Can you repeat what the written G contains a what?
Free semigroup.
A free
On two elements.
semigroup on two elements. So there's something big. G is big, okay? Non-amenable. Specifically, I could write G is non-amenable. or, and this is exclusive, G is virtually solvable. So let me compare these two theorems. They're very different, and I'm definitely not going to go into this. I'm not going to use the Tits alternative. I worked hard to circumvent using the Tits alternative in the proof of Gromov's theorem because it's easy to finish the proof using the Tits alternative, but I wanted not to use it. I wanted to use the softer elementary version by Jordan. Okay? So the Tits alternative tells us the following. Your assumption is weaker, just any group of matrices. All they need to do is act on a finite dimensional space. Okay, that's all. Then you're either non-amenable, meaning giant, or if you're amenable, you're virtually solvable. Any virtually solvable is amenable. In a sense, amenable in some way. It's not exactly, I'm saying, in fact, what I'm going to say is elementary amenable, which is smaller than amenable, less than amenable. Elementary amenable groups are those which are, instead of, I said, remember we closed semi-direct products, the abelian thing, we also take limits. So we close it also in a topological way, like we can take limits of these things. So we can do, instead of doing finite number of commutators going down and ending, you can do infinite many commutators. I'm cheating when I'm saying it's not exact, but you can imagine what I mean, right? You can combine abelian groups and then combine again and again and again. If you do that finitely many steps, you get the solvable groups. If you do it infinitely many steps, you get what's called the elementary amenable groups. Okay, and this is what von Neumann had in mind when he defined what amenable is. He had in mind, like, take the basic building blocks. Okay, you have some structures that you can apply to them, semi-direct products, things like that, and inverse limits. That's all. And then you get amenable.
And going to show that there is non-elementary.
It's not exactly Gergochuk is amenable because it's sub-exponential.
No, there is amenable but non-elementary, right? Or...
Non-elementary amenable, yeah, because it has torsions. Yeah, I don't want to go into that. I'm just saying that yeah, these worlds are complicated. Saying a big or small group, there are many competing notions. They don't always coincide. And so Tits says weak assumption with some nice consequence, but you can get virtually solvable here. Okay, and virtually solvable can have exponential growth. Lamplighter is solvable and has exponential. Okay, permutation group. I said no. Well, forget about that. But lamplighter is solvable. Okay, now the Jordan theorem or the Gromov theorem in the unitary case. This has a much stronger assumption because I'm assuming polynomial growth. I'm not assuming amenable. You can think of this thing as you assume amenable, you get virtually solvable, right? So I'm not assuming amenable. I'm assuming something much stronger, polynomial growth, and much stronger also on the family, on the linear algebra. I'm assuming unitary matrices, which is a more restricted class. Okay? But under this stronger assumption, I get also a stronger conclusion. I get virtually abelian, which is much stronger than virtually solvable. Abelian is like just one-step solving. Right? So this is, I just wanted to mention that you should know that there is a very strong theorem sitting there that you can use, and it's very useful sometimes if you just have linear groups and not, linear groups are very well understood, and this is one of the most important manifestations of this good understanding that we have of linear groups. Okay.
I wanted to ask something about what you said before. Solvable groups are what you get when you take abelian groups and you close it to semi-direct product. So the usual definition that you see, like in say Nemal Gebrim or Galois for solvable group, is that you have a sequence of quotients and the abelian quotients. Finite sequence. And so let's say I have a one-step solvable group. I have a group which has an abelian quotient with an abelian kernel. So
that's two-step, yeah. One-step solvable is abelian, two-step is what you said.
So, yeah. I mean, it's not always that if you have a homomorphism from one group to another, so you have a quotient and a kernel, it's not always that you can make it as a semi-direct product. So
you're right.
In this case, you can.
Yes, in a certain way. You can make it a few semi-direct.
So it
Because finitely generated abelian groups, they are just products, direct products of cyclic groups.
Yeah.
And with the cyclic groups, you can always do this semi-direct product construction, so you do it with step by step. Let's leave that out of the picture. But even if what I said, or even what I said was not completely exact, so you need to think of what extensions mean, and
Yeah.
it's not always semi-direct products. But it's what you have when you have the quotient is something, and then so it's the by operator and group properties. I don't want to go into all of this. It's nice, it's very nice, but it's too many details for one lecture. Okay, so but we're going to use the soft version of Jordan, which actually solved our theorem in the unitary case, right? So if we can somehow get a unitary thing, then we know the Gromov's theorem. So this is basically Gromov's theorem for unitary groups.
Gromov use the Tits theorem or
Well, Gromov can use the unitary one. Okay, you'll see, it's not, Gromov does something much more complicated. Gromov understands this construction, the representation. Gromov creates a representation, and this representation provides the surjective homomorphism or the abelian quotient up to a finite index subgroup. And the way he does it is by taking some nice metric limits of things and doing something very complicated, which converges to a group which sits inside a Lie group. And then he uses the classification of Lie groups. This is Hilbert's fifth problem. So this is very, very deep mathematics, and it will take me a year to just find everything and then teach all the relevant theorems, asymptotic cones, and all these complicated things. And you need to know a lot of group theory to this is much more elementary.
Gromov's proof came before its alternative?
Its alternative is 72, I think. I'm not sure that it came before. I think it didn't come before. I'm not mistaken, it was 70s, and Gromov is definitely 80, beginning of the 80s, 84 published or something like that, maybe 82. Okay. Okay, so let's proof of Gromov. Meaning this one, right? So just the virtually indicable part, the hard part of Gromov's theorem, okay? But using Ozawa and using Jordan, okay? So what do we need to prove? So let G be a polynomial growth group. We need to find a finite index subgroup in G that has a virtual homomorphism, that has a homomorphism, surjective homomorphism on 2Z. Okay, choose your favorite. Choose some mu in SAG2. For example, choose a finite symmetric generating set for G and take U to be uniform measure on that. Right? That's SAG infinity. Right? You don't need even two. Okay, so you see why all the theory I developed. I mean, I like to work in general things because I also think we're harmonic functions, but you don't really need this such a strong assumptions. We don't need, we need such general assumptions. We can work with very, very restrictive assumptions. Mu is simple random walk on some Cayley graph. Okay, and choose. Okay, by Ozawa, we have 1, 2, or 3. All right, we have them over there. Okay, I don't want to rewrite them. Okay, let's see what happens if 2 or 3 happens. Well, first of all, 2, if 2 happens, then we're done. Right? What are we trying to prove? We're trying to prove that G is virtually indicable. That's what 2 says. Okay, so Ozawa already found this finite index subgroup with homomorphism for us. Remember, it comes out of the action on the finite dimensional space, whatever, right? Okay. 3, what does it tell us? It tells us that G has a projection to a unitary group, right? So 3 tells us the following, there exists G mod n U U D C, and by Jordan, right? By Jordan, U is virtually indicable. It's virtually abelian.
G is virtually.
How do I go from this being virtually indicable to G being virtually indicable? Take the finite index subgroup in this guy. What does this mean? Okay, so let's just
Finite and then finite, so it's finite.
Right. This is 3. We're still doing 3, right? So there exists, say,
N is of infinite index.
what?
N is of infinite index. In Ozawa, we said that N was
Yes, I should have written here in Zawa. I didn't write that here U is infinite. That's what we proved. I mean, that's where it was. N was either finite index, then we were in this case, or it was of infinite index, and then we were in case 3. Okay, sorry, I forgot that. I mean, of course, you always have a quotient which is a unitary subgroup. Then just take the trivial quotient. So it's stupid to say that. You need to say something. So that's sorry, I forgot that. Right? So we have this where U is virtually indicable and U is infinite. Okay. Well, I mean, saying virtually indicable means it's infinite. Okay. So there exists.
Know that U is virtually indicable or virtually abelian? Or
Exists U prime.
virtually abelian is virtually indicable.
Right? There exists U prime, which is finite index in U. Okay? And a homomorphism from U prime which surjects onto Z. Right? This is what Jordan guarantees. Some finite index subgroup in U, which has a surjective homomorphism into Z. Jordan guarantees more. U prime is abelian, finitely generated abelian.
what's the name of the subgroup? U prime?
U prime. You want U tilde? Is it better? Everything. Okay, U tilde. Okay. There exists some U tilde inside U.
Can't U tilde be finite?
If it's finite index in an infinite group, it cannot be finite.
Oh, this is finite in
Right.
that group.
Okay. U is the union of finitely many cosets of U tilde, so they cannot be finite. There's also pi, which goes from G surjectively onto U. Homomorphism, right? This is the pi so that the kernel of pi is in. Right? We can take the projection, the canonical projection. Okay? And now let's see. What is, let's write H, define H to be pi minus 1 of U tilde. Spelling this out, this is classical, בפנים algorithm. Okay? So if H, I don't know the fancy name for it, but it's a classical method, right? Just lift it. So what is H of pi minus 1U? This is going to be, right, a subgroup of G, right? And G index H is what? Is exactly U index U tilde.
Wait, where is this from?
זה משפט ההתאמה בוודאות.
No, not this part. How do you know there is a pi? U is a sub.
U is isomorphic to U mod n.
Okay.
I just took there's a homomorphism there. That's what it means. Right? Exactly what it means. Okay?
Yeah.
So H is finite index in G, but if I do first pi and then I do phi, right? And I go from H, where does this go? This goes surjectively onto Z, and it's a homomorphism right? So H is indicable, G is virtually indicable. G is virtually indicable. This shows us that in the cases of 1, 2, and 3, we are fine. Do you agree? Here we are done. And I'm left with case 1. Case 1. What do we do with case 1?
Now we have
Okay.
station.
Now we have to do some control.
Like
No. We already did the work. So let's go to case one. Okay, now we have case one, which is the last thing we need to do. Okay, in fact, I'm going to show you that case one is impossible. Then we're done because, right? Okay, and here, what did I did not really use a polynomial growth. Why did I not really use polynomial growth? Because if I only had amenability, see, if I was only amenable, I would be virtually solvable, which is virtually indicable with tits, right? So I use polynomial in order to use a softer theorem, but this is a subgroup of GLD, right? So just being amenable would be enough, but it's not true that every amenable group is virtually indicable. That's not true. Okay? So I need to use polynomial growth to rule out one. I have to use it somewhere. I have not used it yet.
Wait, the polynomial, but how would we know that it's amenable? Because of polynomial growth.
Sub-exponential growth is always amenable. Okay? But I could, no, but if I replace here polynomial growth with every amenable group is virtually indicable, up to now it works. Up to now it works. Right? Because Ozawa only needs amenable and this only needed amenable up to now. Right? Not to use by Jordan, but it's. So now I have to use polynomial. If I don't use polynomial growth, I'm proving something not true. Okay, good. One is going to see where you're going to see exactly where polynomial growth comes in. Okay, so there exists some h, which is a Lipschitz harmonic function, a non-constant, right? Such that the variance, let's start from the origin, doesn't really matter, divided by t converges to 0 as t goes to infinity. Okay? Like something much stronger holds, but right? Okay. Now here's polynomial growth. G has polynomial growth exercise. This means that the entropy, remember Shannon entropy of the tth step, after t steps, think of a finitely supported random walk. We could have taken mu to be a finitely, right? We said we could take a simple random walk. This can only be a distance at most t from the origin in a simple random walk. This lives in a ball of radius t. Ball of radius t has size at most t to the d, some constant time t to the d, right? With some d because it's polynomial growth. So this means that this is log, right? We had an exercise saying if this almost surely lives in a certain set, right? So this exercise shows that this is less than or equal to the expected log size of the ball of radius, distance xt. So I can look at the distance of xt in my favorite Cayley graph. Okay, I can look at the size of the ball of that radius, right? That's a random size log expectation. We had an exercise in entropy that said if you land in a certain set, you take expectation of that set and log of the size of that bounds the.
Probably we didn't say the corollary of that, but that any sub-exponential growth has entropy 0.
Any sub-exponential growth is entropy 0. I think we mentioned it. But, it's true. Okay. Okay. So log the size of the ball bounds it, and if you don't trust me on this, think of simple random walk. We could have taken simple random walk in this proof. And this is deterministically of size at most, distance at most t. Deterministically lives in the ball of radius t, which has size at most constant e to the d. Okay, so this thing, further exercises to show that this, you have, fast enough decay. This will be of constant,
T, right?
log t, right? So there will be a constant which depends on d, which d is the polynomial growth. Okay, it's just some fixed number times log t.
What is the correlation between the polynomial growth and our mu? Because we take any mu, not just simple.
Yeah, but I take mu and it has second moment with respect to some Cayley graph, which means with respect to any Cayley graph. It just changes the constant. It doesn't change. Okay. But think of simple random walk. I mean, really, I could have said, okay, start. It just makes things more complicated, but I just need some u, right? I'm working with my favorite one. And I could have taken simple random walk on a Cayley graph, then everything here is exactly what's written. Okay? The assumption of polynomial growth is exactly this. This is exactly polynomial growth. Okay, in fact, it's equivalent, but that's maybe more complicated. Okay, but what does this mean? This means that if I take h of xt minus h of xt minus 1, okay, this is a derivative. What is the derivative of log? 1 over t, right? So this is less than or equal to constant over t. Wait, you're saying discrete derivatives, right? Okay, so not for every t, but for infinitely many t. You agree? So infinitely often, infinite IO means that infinitely many t, this inequality holds. Right? Assume the opposite. Assume it doesn't hold for infinitely many t. This means that this is bigger than this constant over t from some t0 onwards. If you sum the telescopic sum, you'll get that this is bigger than some other constant times long t. So maybe by changing this constant, right, you get. Okay. So it's always true that if you have a function, discrete function, and you take the derivative, then it doesn't hold for everything, but it holds for infinitely many at least. Okay, right? Because if you assume the opposite, then you get the lower bound, which is the function that you can integrate. And it's just a connection between Riemann sums and. Okay. Anyway. Okay, but this is an easy exercise. Okay, so we have this for infinitely many t, not everything, but infinitely many t. We still can take limits along that sequence. That's all we need. Ah, wait. Now this is going to contradict something.
In the discrete derivative, you don't have to divide it.
What?
In the discrete derivative,
Yeah.
you have to divide by xt minus.
Well, the difference is 1.
You divide by t minus t minus 1.
Yes, by t.
It took 1 step. I need to change. Okay, let me write. This is C prime. It could be a different constant, but it's just universal. It's not. Okay, so I'm continuing the proof of this theorem, right? So, okay, by Poole inequality, used again. Okay, used again. And now we use the Poole inequality. Have the following. H of x1 minus h of x0, which is 1. In absolute value, expectation, all of this squared. This is the Poole inequality. Okay, I'm just writing it down. True for every harmonic function, specifically for my h here. Okay, because it's a harmonic function. This is less than or equal to 4 times the variance of h of xt times the entropy difference. Right, this was the Poole inequality. Related the variance, the entropy difference, and the some form of the change around the origin. Right. Okay. This is exactly the Poole inequality. Now let's see. So for infinitely many t, what do we get? This thing, okay, is less than something. So the square here, this thing, I'm not going to write it again, okay, is less than or equal to 4 times the variance, right, times some constant, c prime, divided by t.
And it's then 0, then it's constant.
This thing, if this converges to 0, right? So if we if we have case 1, remember case 1 was saying that this converges to 0, right? This converges to 0 as t goes to infinity, and even a subsequence is enough, right? Then what do I get?
Take this one.
Well, so in case 1, what I get is that the expectation, square I don't need anymore, of h of x1 minus h of 1, all of this is 0, right? There's no t on that side. But this is a non-negative random variable which has expectation 0. This means it's almost surely 0. So h of x is h of 1 for every x in the support of mu.
It generates.
That's it, mu generates. So now I can continue this game, right? Okay, because I could have done this also around any any other point, right? Remember, I could have taken the cool inequality around any other point. Maybe we should have written it that way. So I repeat this, say with a neighbor of one, I can do it in any steps. And so let's say it's an easy exercise
I think we've done something similar.
to now prove, yeah, this is basically the maximum principle. I mean, you cannot have a maximum. If you're constant, if you're constant somewhere, if a harmonic function is constant somewhere, it's constant everywhere because it's an easy exercise to now prove that H is constant contradiction.
If it is symmetric with second moment and you do convolution with itself, it still has a second moment? No.
Yes.
Okay, it's another proof. So we can do the same thing for mu to the power of n to any n. The same proof.
Yeah, right. Okay, so you're saying a different way of, so I could have done this around any origin. So H is constant around any guy, and this means I can go with a path word constant to any place. That's one way. The other way is what Nadav is suggesting. Let me explain the proof. He's saying, okay, think of, instead of writing here x1 minus h1, H is also harmonic with respect to mu to the n. I could write here, I could write hn, right? I could write h of xn, right, for any n. It would still be true. I would need to do a tn. I'd need to do like something, but it's still true, right? And this, if this side goes to 0, right, then I get that h of xn is almost surely always equal to h of x1, h of 1. And if I, for big enough n, I can get with positive probability any element here. So this will be bigger than the difference between those two elements in absolute value. And so I get that everything is 0. Of course, I mean, these are all equivalent ways of seeing why. I mean, it's basically boils down to the maximum principle. Harmonic functions cannot have maxima, local maxima or local minima. Right? They have to have them on the boundary, which in our case is at infinity. And okay. So that's it. So we proved Gromov's the hard part, right? Because we ruled out case 1 and the other 2 cases had a virtual law. So this completes the proof. And then we have one more step to do, and that's show that this implies the complete Gromov theorem, which will be the end of today's. Take a 10-minute break. Okay, so the next step in Gromov, final step in Gromov's theorem is to prove. So we use Gozawa. I think you should see it was very, very clear where we used polynomial growth. We used it in the Kuhn inequality in showing that this is 1 over t. Okay. Now I can get better. I can get other estimates for non-polynomial growth, but I don't know that the rate. If I had a 1 minus epsilon here. What does 1 minus epsilon here correspond to? This corresponds to growth instead of polynomial. It corresponds to radius r growing like r to the epsilon. Okay, when you take the derivative of this and then you take log, then you see that this is what it corresponds to. And if you had such a thing here, then and you knew it went to 0, then you could get this, at least this part of Gromov's theorem, you can get for even larger growth. This would be a major step towards the gap conjecture that I mentioned. Okay. The problem is that how did we get this? How did we get this part in Ozawa's theorem where it has 1 over t? We got it using the ergodic theorem. 1 over t came, remember, from 1 over t Birkhoff sum, right? And this the ergodic theorem cannot be quantified. It's just not true in general.
This is the boundary. We had the polynomial growth because of this one, because we wanted 1 over t that we got from Ozawa's theorem from.
It miraculously works that you get 1 over t from the polynomial growth, and it's enough for the ergodic theorem. And you cannot improve the theorem, at least not using the ergodic theorem. You have to replace the ergodic theorem component there. You remember we had this AT, which was the sum of the C with itself. We have to replace that with some other component in order to get a better estimate.
The better estimate for what?
We want to prove that any group of small enough growth, but
We
Something
want-
super
we want-
polynomial is virtually indicable. I mean, there's a conjecture,
For
right?
the indicable, not for, because virtually nilpotent is done.
Not for polynomial growth. I want super polynomial growth. I want to say, okay, the conjecture is that there are no groups of small enough growth. So the conjecture is that if you have a group of e to the r to the growth like this, where epsilon is less than 1/2, then it's actually virtually nil. Now, this conjecture is a very strong conjecture, and in fact, you can take a weaker conjecture, which would be any group that has growth like this is virtually indicable. We know that every polynomial group is it, right? We know that virtually nilpotent is polynomial. So a weaker conjecture would be any group with this type of growth instead of polynomial is virtually indicable. That would already be a major breakthrough. And in order to do that, there's one step here where everything works. Everything we did works. There's one step that does not work, and that is that this has to go to zero. So we can rule out case one. Okay? If you can prove by some other way that in a small group in this sense, okay, there is no such thing as a Lipschitz harmonic function that has sublinear variance. If you could rule case one out in some other way, then we're fine. And it's true. I mean, it's true because if these groups are virtually nilpotent, then we know that there are no sublinear variance. Okay, so somehow we need some other way of doing it, either quantitatively or in some other way.
Ariel, in Gromov group or in other intermediate growth groups, we know the growth rate exactly.
Bigger than, yeah. There's a deep reason why 1/2 appeared in that stretched exponential, and they all have for Gromov, there's even exact the exact epsilon you need to put there, strictly bigger than 1/2, and you know what you put.
There's nothing about exactly 1/2 that people know.
No, we don't know. The smallest group, there's a version of Gromov group. There are families of these type of groups, and there's a version. In a certain sense, they're all the same construction, okay? But they have different. And there's a version of Gromov, by Bartholdi, who created a group which has a smaller alpha, a smaller epsilon there, but nobody has, as far as I know, nobody has reached exactly 1/2. So there's no, but 1/2 comes up from some other considerations. So all of the constructions have a certain property, and that property implies growth at least e to the r to the 1/2. You get that? Okay, e to the r to 1/2. What is that? That is the function that governs partitions of the integers, right? How many ways can you partition n? It's right. This is something Hardy Littlewood or something like that. Like it's a classical number theory result. It's e to the square root n. So e to the square root n comes from the partitions. Okay, the specifics of the different groups you have to. So it's just a lower bound because partitions give a lower bound. But that's something much. Okay, last step of Gromov's theorem. So theorem. Gromov. Every polynomial growth group B is virtually nilpotent. Expecting to do this like a month ago. Too optimistic. Okay. Let D be such that ball of radius r, should write maybe for some fix telegraph D, let D be such that, let's not do this. For a group of polynomial growth, G, write the degree of G to be the non-negative number say it has to be an integer, such that in a Cayley graph, G, some Cayley graph of G, the ball radius R has size at most some constant times R to the degree of G. This is what polynomial growth is. It means that you can find a number, a polynomial, that bounds this up to a constant, right? Now, notice if you change the Cayley graph, what changes is this constant. This number will not change, okay? You only get a different constant. Okay, so this is a group invariant. It doesn't depend on the specific choice of the Cayley graph. This is what polynomial growth is.
The degree of
The degree of the polynomial growth, yes. It's exactly the degree of the polynomial. Okay? Now, proof by induction on D. This is Gromov's induction, and this is the same induction used in all the papers. All the papers that, all the proofs of Gromov work hard to do the previous theorem that we said, that just virtually indicable. And then the induction is same one that appeared in the original. Okay, proof is by induction on D. If G is infinite, then this degree has to be at least 1. Do you agree?
Otherwise it grows like a
Right?
constant.
Because I mean, if you have a ball radius R, right? And they grow, you know, infinite group, so you have to have at least R guys inside the ball, right? Otherwise you cannot get to distance R, right? So there is a path going from distance R to the origin, and each one of those has at least one vertex, so you have to grow at least linearly. Okay. So as soon as the degree goes below 1, right, we know that the group is finite. Okay. This is basically the base case. Okay.
So
For finite, there is nothing to prove. Okay.
There is no degree half or something like that?
What?
Do you have degree 0, degree 1, and then you get on integers, or can you have
A
degree?
posteriori, we know that everything has integer growth, integers. The degree is always an integer.
Oh, okay.
But this is a stronger theorem by Bass and Givalch, and they use the fact that you have the nilpotent subgroup sitting inside.
Oh.
So you analyze nilpotent subgroups, you can determine the exact integer and the exact degree, and it turns out to be an integer, but we're not assuming it. Okay? So if G is infinite, degree is greater than 1, this is basically the base case now. So by the previous theorem, right? G is virtually indicable. It has polynomial growth, right? This will prove every virtual indicable group has, every polynomial growth group is virtually indicable. So there exists a finite index H. Okay? Such that H is isomorphic to Z acting on some N. That's what indicable means, right? We said it. Okay? Now H, this is an easy exercise. H is finitely generated, and the degree of H is equal to the degree of G, meaning that H has polynomial growth. It has exactly the same growth. Finite index subgroups have exactly the same growth as the original group, up to constants. So this means that balls only change their size up to a constant. So this means that the polynomial stays the same polynomial. Okay? But then, by a previous exercise that I already erased in the previous hour, we know that N is finitely generated, right? So, okay, this is basically Rossette's theorem, right? If you have a quotient by which is abelian and sub-exponential growth, this is polynomial growth, then n is finitely generated. But not only is n finitely generated, the degree of n is at most the degree of h, which is the degree of g, minus 1. Do you agree? This is exactly allowed induction. See, this is beautiful.
So this is the second place where you use the polynomial growth, of course.
Yes, 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 yes.
Not like if you could just prove that, I don't know, you
No,
know
so-
that every free group has is virtually indicable, but it doesn't mean that.
Gromov's theorem uses, the proof uses polynomial growth twice. One to prove that every polynomial growth is virtually indicable. And this I said, I showed you where you need to remove the piece of the ergodic theorem, place it to something else, generalize it to larger growths. And then if you still wanted a gap conjecture, every group of small enough growth is virtually nilpotent, you would still need to replace this induction with some other procedure. So this step does not work for non-polynomial growth. We use the polynomial growth here. And this is a project I actually have ongoing. I think maybe we can do something there. I haven't managed to do it yet. Okay, by induction, n is virtually nilpotent, right? That's what the induction is telling us. Okay? N is virtually nilpotent. This implies that H, which is isomorphic to the Z extension on N, remember I told you that this implies that this thing is what? Is virtually solvable, right? But Milner-Wolf tell us that any solvable group is either virtually nilpotent or of exponential growth, right? So there exists some subgroup inside H, say K, finite index, such that K is solvable, right? And of polynomial growth. You can think of Milner-Wolf as Gromov's theorem for solvable groups. It tells you virtually nilpotent or exponential growth. That's kind of, it's a wider thing because you're in a much more structured situation. So if I have a solvable group of polynomial growth, it's definitely not exponential growth, right? So by Milner-Wolf, K is virtually nilpotent. See, I want you to notice I'm using virtually all the time. There's another finite index here, another finite index there. Every time there's a finite index that I'm losing, but it doesn't matter to me in terms of what I want to prove at the end of the day, because finite index subgroup of a finite index subgroup is also finite index in the big group. Okay? So K is virtually nilpotent, but K is finite index in G, so G is virtually. Right? Because H is finite index in G, K is finite index in H, so K is finite index in G, meaning that the subgroup in K, which is nilpotent, is finite index in G as well. So G is virtually nil.
It seems that in a sense, all we did in this course was to omit case one, right?
Wait, did we use the
Well, we've
induction?
developed the machinery to do to do this dichotomy. I mean, the theorem holds in itself, and it's an interesting theorem, and it's an interesting theorem in the sense that I want to go to bigger than polynomial growth and say something. And I showed you exactly, there's one exact piece where you have to replace this ergodic theorem piece. Let me write down. I'll end with the gap conjecture and explain what actually is. So this is the end of the theorem, okay? That proves, right? We start with an arbitrary thing. We managed to go down in the polynomial degree. Oh, we know that everything of degree at most n is virtually nilpotent. But this means that everything of degree at most 11 is virtually nilpotent. And then I didn't say, what happens if in the one, it's a little subtle. Let me just mention it. I'm not gonna write anything. What happens if the degree went down by one and now and this was less than one? So what happens if degree of H is like 1.5, right? We went down by one, you go to half, right? Or something, 1 minus epsilon. So degree of n strictly less than one, we said means n is finite. So then we don't have this, well, we have this situation where n is a finite group. Okay, so maybe n is virtually nilpotent, I should write, or, I mean, virtually nilpotent includes the case where you're virtually nothing, okay? So finite. And n being finite implies that z acting on n, okay, will actually be virtually a billion. But so it's specifically virtually so. So everything is true, but you have to take care of the finite n case. You have to be careful about the finite n case and do it properly, but it's true.
The base of the induction or something.
Yeah, this is kind of the base case. It's kind of the base case. Okay, so this is good. So let me give a summary of what's going on. I want to talk about the gap conjecture and provide a summary of what we did. Lecture is Gregor-Chuk's gap conjecture. Let G be a group of growth, which is at most. What is growth? Growth is the asymptotics of the function that maps the radius to the size of the ball. So this is at most R maps to e to the r to the alpha for some alpha less than a half. You have some fixed alpha which controls your growth. This means that I can act up, put a constant in here, put a constant out here, the same equivalence class of functions. Okay? An equivalence class of monotone functions. Then the conjecture says G is virtually nil, which means actually of polynomial growth. Right? What is this? This is the gap. There are no groups. So this is in a different way of saying this. There are no groups with growth in between polynomial and some stretched exponential. Okay? Now replacing this with any super polynomial function is basically wide open. The only thing we know, we could put the function here, we could put R maps to, what is polynomial? Polynomial would be e to the constant log R. Right? I'm allowed to put constants here. This would be polynomial. And you can make a correction here of log R to some epsilon. There is some known epsilon, and this is known. Okay? This is done by really quantifying Kleiner's proof by Terry Tao and Yuda Shalom. They quantified the Kleiner's proof, which is a different proof I could maybe mention at some point, but just have this small log to the epsilon correction. You know, so there is some gap known, but it's very, very far from what we believe is true. So anything above this, in fact, giving even a different proof of this, even something smaller than that, super polynomial, you had a fundamentally different method, be very, very interesting. And in fact, a weaker conjecture, so the weak gap conjecture, any group of small growth, whatever that means.
What do you mean by actually of poly growth?
If it's virtually nilpotent, then it actually has polynomial growth. As soon as you have growth below some super polynomial function, you drop down to polynomial growth. You cannot have a group which has something in between.
You want to go a little bit upstairs than of polynomial growth to get that.
There's a gap. You list all the functions, all the growth functions. After polynomial, you have to jump above e to the square root n. Okay, that's a big jump. Okay. So any group of small growth, take your favorite definition of small growth. It shouldn't be this one, but
Once
this is
again,
small.
where does the square root of n come from? This is
It comes from partitions. It comes from partitions. Partitions give a lower bound on all the known constructions of intermediate growth groups. And it fundamentally comes from some group properties that all these groups share. Okay. So any group of small growth is virtually indicable. Right? So this would say we had two steps in Gromov's theorem. One is to prove that every group of polynomial growth is virtually indicable. Second is to do an induction on the polynomial growth. This is okay, do step one. Do step one. This would be already a huge breakthrough, I think. I mean, this would definitely.
Do we believe it's true?
Yeah. I mean, everything. You believe the gap conjecture. Okay, if you believe the gap conjecture, then you have to believe in this. This is a weak gap. This is weaker. It's logically implied by this one because every virtually nilpotent group is virtually indicable. Okay. Now, let's say what is missing. What would imply this conjecture? What would imply this conjecture? Okay. We can write it differently. Conjecture. If G has small growth, and again, by small growth, I mean plug in the function that you think works, okay? Which should be this one, but maybe you want to work with a smaller one for some technical reason, okay? If G has small growth, then any H in L Lipschitz harmonic function G mu or some mu, I don't care. Okay, in fact, let me do for some finite support mu, in fact. Okay. Let's write mu in SA infinity. So there exists, I should write it down. If G has small growth, there exists a mu in SA G2, okay, such that any Lipschitz harmonic function that has sublinear variance take any Lipschitz harmonic function that has sublinear variance is constant. We know this is true for virtually nilpotent.
Okay,
So this is logically implied by that, because by virtually nilpotent polynomial growth, we know this has to hold, right? This is exactly the case one. This says, what this conjecture says, if you have small growth, you can rule out automatically case one. And this implies this conjecture, okay? And in fact, they are equivalent. I mean, well, they're not exactly. Okay? We want to say something else about this? Yeah, let me say something
well,
else. What is the question? These are hard conjectures, okay? This is not a PhD problem. I mean, if you have an idea, then we can, anything on the way to this would be super interesting.
Just Liran.
Yeah.
No, but like,
So do I. But
can you explain again in the third conjecture what is the gap like? Once again.
it just put the actual gap that should be here is the actual gap that is here.
No, not the gap, but like what do we know so far, and what is here? Like the
We know this is true for polynomial growth because we use the ergodic theorem to get this t here. sorry. We know this is true of polynomial growth because in polynomial growth, 1 over t for infinitely many t comes from the entropy thing, right? So you can rule it out.
And you want small growth, but still leave the t downstairs because you want to use the ergodic theory?
I don't know what I want to do. One way to do it is to replace the ergodic theory thing with a better,
No, but if
with
we
the
want to use,
existence of a better, something with better than sublinear. So it has maybe linear variance, but when you divide, sorry, it has not just sublinear variance, but quantitatively such. So it has variance less than t to the some power, which is less than 1. If you can control the variance quantitatively and still say that it goes to 0, okay, then then you will get for small enough growth that the cool inequality tells you that any function like that is constant. So
but if you want to use the t over there, that's because you want to use the ergodic theory. The ergodic theory.
I want to rule out the case 1 in Ozawa, which comes from ergodic theory. Yes. I want to rule. Maybe there's a different way of ruling it out. Okay, let me show you. Okay, theorem. This theorem is by, okay, I won't write down the names. This is by, in the right order, okay? Dan Perl, which is a former student of mine, Matt Toynton, Tommy Rovich, and myself. Okay, so it's in a paper with all 4 of us. The theorem is, if the dimension of the Lipschitz harmonic functions, G mu, is finite, okay, then any h in Lipschitz harmonic functions G mu, this is true for any symmetric, u here is any symmetric. I think we did it for for exponential tails. So let's so if you have exponential tails and you look at the dimension of this space and it happens to be finite, okay? Then if you take any function in this space such that the variance is sublinear, then what? H is constant. So one way to do this conjecture is to show that if you have small growth, the dimension is finite. Okay, the dimensions of Lipschitz harmonic functions is finite. Okay. One of the exercises I'm thinking of giving you on the final exam is to prove that the dimension of Lipschitz harmonic functions is finite for nilpotent groups. Okay, but in a structured way. I mean, not just like that as a statement, but just to give you a why should I even believe this is true? Why should I even believe this is true? Okay, so theorem by Kleiner. So this is Kleiner. How did Kleiner prove? It was before Ozar. How did Kleiner prove Gromov's theorem? First, what Kleiner did was Kleiner proved that if G has polynomial growth, and here I really cannot generalize it. I tried a long time. G has polynomial growth, then he proved it for finite support mu. He then generalized it for mu in exponential tail. Then for mu in SAG infinity, the dimension of Lipschitz harmonic functions. In fact, Kleiner proved much more than this. Kleiner proved that, remember we had h of k, right? K grows like a k polynomial, so not just Lipschitz. Like bigger spaces, they're all finite dimension. But it's enough, it's enough. So what Kleiner does, you prove this, right? Then Kleiner didn't do it this way, but how would you go about proving Gromov's theorem? You start with polynomial growth, you prove that this dimension is finite. It's not a very difficult, it's a combinatorial proof. It's not a very, very difficult, I could have taught it. Okay, but it's more subtle and I think conceptually it doesn't capture the want to say the right ideas. It captures a different type of set of ideas that I think don't generalize to the non-polynomial case. And these ideas, except for the ergodic theorem, all generalize to the non-polynomial group case. They're all quantitative except for the ergodic theory. So, but if you want to go with Kleiner's proof, what you do is you prove that the dimension is finite. Then you use our thing, which came after Kleiner, but then never mind, he didn't use it. He did something. Then you use our thing to say, oh, then I have this property that any sublinear, that I don't have non-constant sublinear variance harmonic functions. Meaning I don't have case one in Ozawa, meaning any group of polynomial growth is virtually indicable. Done. That's Gromov's theorem. Okay? That's the hard part of Gromov's theorem. The rest is the induction. Okay? So you see that you can also go in this way. Okay? The reason I'm explaining is that there might be a different way of ruling out this thing that does not replace the ergodic theorem, but it just says small enough groups. So so conjecture, right? I can give you a weak conjecture. If G has small growth, I need to go. If G has small growth, then the dimension of Lipschitz harmonic functions G mu is finite for some mu in say G infinity. If you do it for a bigger G mu, then maybe I don't believe the bigger mu, the less moment should help you. It should actually be worse, right? Okay. When you take less moments, right? For example, we know that if you have a non-virtually nilpotent group, then there's always one where you have bounded harmonic functions. This will not have any moments, not anything, right? Okay. So if your bounded harmonic function is a dimension of the bounded harmonic functions, we said is always infinite, right? So this already implies Liouville, so you have to be careful. But just find some measure, some simple random mob, some exponential, I don't know, find someone which has a finite dimension of Lipschitz harmonic functions, just under the small growth assumption. If you do this, you've basically given me the weak gap conjecture. You've made a huge breakthrough. You can somehow connect growth to the dimension of Lipschitz harmonic functions. And this is what Kleiner does, but I want a different way of doing it. Okay?
Well,
Okay, that's it for Gromov, and next time we start bounded.
היום